Well, hi, thanks for watching. Before you start in this part of the notes, I do want you to look at the sentence at the top because you should have already done the electron configuration puzzle, which is kind of a teaser to get you just the idea of what we're going to be doing here in this section. So just to kind of set the stage here, in the first part of the unit we looked at just what's in an atom. Like what are these little particles? We call them subatomic particles because they're smaller than the atom. So we've got protons, neutrons, and electrons. And we talked about their mass and their charge and how we describe different atoms based on those things. But this section is all about the electrons and where they're located. It turns out most of the important properties of all of the elements, what makes hydrogen explosive, for example, or what makes iron so easy to rust, has to do with where the electrons are located. So that we call that the electron configuration. So we described in the first part of the unit that they're located in these things called energy levels. And you can kind of think of those as like orbits around the nucleus, where the nucleus might be like the sun in our solar system. So those are things that should be already familiar. So for example, protons and neutrons, we said in the nucleus, and electrons located in what's called energy levels. Now you'll hear the energy levels referred to by other names as well. In some textbooks and other references, you'll hear them called shells. You'll hear them called orbits. You might hear other names as well, but I'm just going to use energy levels. And just to remind you, although we never draw them this way, the nucleus is a tiny, tiny, tiny little piece in the center of a much larger atom. Now, of course, they're not large, but the nucleus is just so much smaller. So the electrons are not that close to the nucleus in terms of relative size. Okay, so now we're going to look at how the electrons are spread out in the energy levels. So as you remember from the little diagrams on the puzzle, these energy levels, or the orbits, there are up to 7 of them. And that's just a little fact that we know that any of the electrons we've ever found, when I say we, I mean scientists, they've been found somewhere in the first 7 energy levels. That doesn't mean there aren't more. We've just never found any elements that have electrons in anything higher than the 7th one. So when you look at those little patterns on the puzzle, you notice the one closest to the nucleus never had more than 2 electrons. And that's because it's only able to hold 2. You can think of it as like being closest to the nucleus. It's the smallest one, and it just doesn't have as much room. And that's sort of kind of true, but it's not a bad way to think about it. The next one, if you look at any of the ones with more than 2, you'll never see anything greater than 8 in the second energy level. So it can hold up to 8. And then the next 8, if you would have up to 18 electrons to put into an atom, the next 8 would go into the third energy level. Now it turns out it can hold more than 8, but for reasons that are a little bit more complicated than I wish to get into in this class, we're only going to describe up to element number 20. So the next 8, from numbers 11 up through 18, go in the third energy level, and then the next 2 will start filling up the fourth energy level. So again, if you look back at that little puzzle arrangement, you'll see element number 20 starts filling up, or 19 rather, starts filling up that fourth energy level with the next 2. And I said it gets really weird after that. I'm not going to expect you to know anything other than the first 20 electrons. And I'll do an example of this in just a moment so you can kind of see what I'm going to expect you to be able to do, and then you'll have a chance to practice it as well. So I'm going to give you an important hint, and this may summarize everything that's important to know about electrons. I talked before about where those electrons are has everything to do with the way that these elements interact with each other. Why some are very explosive, why some react easily, why some really don't do much of anything at all. So I'm going to refer to the periodic table, and I want you to notice across the top, the columns are numbered 1 through 18, but they're also numbered with Roman numerals, 1A, 2A, and then we get these B elements here, and then 3A, 4A, 5, 6, 7, and 8A. 8A all the way here on the end. So I only expect you to know about the A elements. This big block here We call these the transition metals, or sometimes we refer to these as the B groups. They're a little complicated. They don't exactly follow the rules, and so I won't expect you to know those. Someday maybe you'll take a Chem 1 class, and they'll expect you to learn a little bit more about the transition metals. But for the A elements, there's a nice little rule, and this was something I'd hoped you would see when you did your little puzzle. And that is that, I'm going to go in a little different order, that the row number or the period number, so those numbers I just gave you before are called the group numbers. You see that written here. But the period numbers are the numbers down the side. It tells you which horizontal row that it's in. That row number will tell you how many energy levels have electrons in them. So if you look at the puzzle, you'll see everything in row 4 has the last electron in the 4th energy level out from the nucleus. And that's true all the way out to the 7th one. So that's why those ones with 7 energy levels were so big. Also determines how big an atom is, just how much space it takes up. But the group, or the vertical column that it's in, tells you how many electrons will be in the outer energy level. So if you look at the group 1A elements, starting with hydrogen all the way down through francium, they all have 1 electron in its outermost energy level. And that's true for 2A, and then again, we'll skip the transitions, and then in group 3A, starting here with boron on down, those all have 3 electrons in their outer energy level. Okay, so I've inserted a little interruption into the video, but we'll get back to the original one in a second. When I made this, I had a different periodic table, and you may be using something different than what you see in the video. Now, all periodic tables look a little different, but they mostly have the same important information. The one thing that I want to point out is your periodic table may not have the Roman numerals with the A's and the B's in it. And so you'll have to get used to the more common method of doing it now, which is just like I have here on this one, group 1 all the way through 18. Okay? So it's still true that the only elements on the periodic table that follow the rule about their number of valence electrons are the ones here, 1 and 2, and then 13 through 18. So this big group here in the middle between 3 and 12, they don't follow that rule. They're known as the transition metals, and here's a little color-coded box to point that out. Anything here that's kind of pink, including also these sort of gold and green boxes down here, those are all collectively known as the transitions, and so they don't follow that rule. So I'll never ask you in here to predict the number of outer electrons. However, on this particular periodic table, if I'm going to zoom in here and you can see it a little bit better, you can always refer to the numbers up here in the upper right of each box. So for example, we're looking at indium here. And these numbers are really helpful because they actually show you explicitly the number of electrons in each energy level. So you see for indium, we have 2 in the first, and then down from there we have 8, and then 18, another 18, and then 3. Now the 3 you could already predict because it's up here in group 13, and group 13 is the 3rd group that follows the rule. So again, we kind of imagine skipping 3 through 12. So when we count groups to get the number of valence electrons, it's 1, 2, and then all the way over here to get 3. And that's why indium is included in that group 13, because it has 3 outer electrons, as does everything else here from boron all the way down. Okay, so that's just something you'll have to get used to. It's not a hard thing to know. You just have to kind of get used to it. So I'll kind of pause this little insertion here. We'll get back to the original video. Thanks. So this provides a nice little shortcut if I only ask you for that kind of information. So for example, let's just do this for practice. Element number 4. So get a periodic table and take a look, or you can look at mine here. Here's element number 4. Its name is beryllium. It has the symbol Be. I'll remind you that the first letter should be capitalized and the second letter lowercase. I'm going to ask you which is the outer energy level in beryllium. So to find out which is the outer one, you're going to go straight across to find out what row number it's in. horizontal row 2. Now be careful, when I say row, I'm talking about the horizontal row. So that means the outer energy level is level 2. And how many valence electrons? Now valence electrons, I referred to it up here, those are the ones in the outermost energy level. So now we go up to the top of the column, and you see how it's in group 2A. That means it has 2 outer electrons, or 2 valence electrons. So this just happens to be a case where the outer energy level and the number of electrons happen to be the same. That doesn't have to be the case, though. Let's look at element 33. Find it on the periodic table. I'm getting a little bit of a glare from my light here, but I'll hold it so you can see it. Element 33 is arsenic. You may have heard of arsenic before. It actually can be used as a poison. Its symbol is AS, lowercase second letter. To find out which is the outer energy level, you go straight across. You don't really need to go straight across, but if you just find out what horizontal row it's in, we're in row 4. You can also just count down. Now be careful when you're counting down to arsenic, because row 1 doesn't have anything right above it. So outer energy level 4. And how many valence electrons are in arsenic? If we go straight up, be careful, it's not 15. Most periodic tables will have these numbered 1 through 18. I like to use the Roman numeral grouping name, so it's VA. Now V in the Roman numerals represents 5. If you don't know Roman numerals, you're just going to have to ask me for help, or you can Google it. But that V means 5 valence electrons. So I maybe ask you to stop here, maybe just pause the video, and try to find the information here for 55 and 117, because it's done just the same way, and then pick up again on the video and I'll show you what the answers are. Okay, spoiler alert, here are the answers to these. So cesium was element 55. It's in horizontal row 6, and it's underneath group 1A. Element 117, now on some new periodic tables you'll see that this actually has a different name, but on ours UUS is the symbol for it. It is in horizontal row 7 and also in group 7A. So this is another one kind of like beryllium that had the same outer energy level as it did the number of outer electrons. So last thing I want to show you, and something I'll expect you to be able to do, is to be able to draw the electrons in up through element number 20. So I gave you these rules before on the first page, and that just described how many electrons each of these energy levels can hold. So I want to show you how I want you to draw these. So let's use chlorine as an example. So you first have to find chlorine. Our periodic table has the names on it. So chlorine is element number 17. If you do it enough, you get used to the symbols and you know right where to look. So its symbol is Cl. So we put the symbol on what we call the Bohr model. We put the symbol right here in the middle. Capital C, lowercase l. And then what I've got here for you, just easier than you drawing it, is I've got the energy levels drawn. So you're just going to place the appropriate number of electrons in each of those energy levels. Now use a little care when you do this, because I want to be able to count them to check that you've done it correctly. So first of all, how many electrons are we going to put in there? Notice that chlorine is element number 17. That's the atomic number. That tells us the number of protons, but in a typical atom, that also tells us the number of electrons. So when we're done, we should be able to be up to electrons equaling 17. But let's put them in a little at a time. So back on page 1, I told you that the inner level can hold 2 electrons. So what I'm going to get you to do is to draw an electron there, just like a heavy dot, and one down here. I kind of like them apart from each other so I can kind of tell them apart. So there's the first 2. Now the second energy level, I'll remind you, can hold up to 8, and then it's full. So we're going to draw 8 around here. Now what's the easiest way to draw 8? Well, you draw 1 on the top, bottom, left, and right, and then you just put 1 in between each of those to kind of spread them out evenly. And that's an easy way to get 8 to fit around a circle like that. Now how many go in the next one? Well, on the front page I told you that the next 8 also, they'll stop at 8, and it goes into the third energy level. So we're going to do something very similar there. But wait a minute. If I put 8 more in here, I'm going to be up to 18, and that's too many. So here's the way you know when to stop. You see how chlorine is in row 3 and column 7. That means I should only be going out to the third energy level, and I should only have 7 valence electrons, or 7 electrons in the outermost energy level. So I'm not going to draw all 8 into there. So here I've got 4, and I'm going to put 3 more in. I don't have to be super careful which ones I put them in. I'll just put them in between maybe these. And then the one I'm going to leave blank is right here. If I had one more electron to put in, maybe if this were the element called argon, then I would put it there. So always stop and make sure that when you're done, you count a total number of electrons equal to the atomic number. And this is for, again, what we call a neutral atom, kind of an atom that just normally exists. Now later we'll talk about why some atoms would gain or lose some of these electrons, but for now we'll just say it's equal. And that is what the Bohr model looks like. So I want you to be able to do that up to number 20. And if I had 20, I'd have to put 1 more here in the third energy level, and then I'd have 2 in the fourth energy level. And then after that, again, it gets a little weird. You can look at that puzzle and see what it does, but I'm not going to expect you to know that. So hopefully that's enough practice, and I've got some more practice for you to do to get good at this. It's not a hard thing. You just kind of have to learn the rules. So make sure you get some help if you need it. Otherwise, good luck. Thanks for watching.